So in the last class, we talked about multiplexers, right? And you can use multiplexers for multiplexing between different inputs. If you have multiple inputs and then you are at any given instant of time, you want a single input, okay? Then you multiplex. You use a multiplexer and then you apply the right control signal to get the appropriate input out of the multiplexer, right? That's one way of using multiplexers in your design, and that's most of the time. That's the most predominant way of using multiplexers in your design, where, for example, you want multiple functionality from a piece of hardware. And this, in one example we have shown in the last class. The other way of using multiplexers is to actually map your functions onto the multiplexer. Okay, you can do that using the K-map approach. In the last class, we talked about the K-map approach, where you divide the K-map. So you have a function, you draw the K-map corresponding to the function, right? And what do? So actually, let me finish the problem that we have taken in the last class with the multiplexers. So you're given a function f, and that function was this one, right? F is a function of a, b, c, d. You have 4 inputs, and the given function was sigma m 1, 4, 5, 7, 9, 12, 13. 5, 7, 9, 12, 13. Okay.
Professor,
Yes.
are you going to include multiplexers in the exam?
Okay. So whatever we have covered until last class, last Thursday, right? So
Got it.
for multiplexers, again, because we haven't had an assignment on that yet, so you can be safe to assume that you will not be having a multiplexer as part of your long answers. However, you may be tested on the concept on the short answers. Okay, does that make sense?
Yeah, it does. Thank you.
Okay. All right. So that's your multiplexer. That's your function, and we want to implement that function using a 4-to-1 multiplexer. How would I do this? Again, recall the design approach, right? Here's your 4-to-1 multiplexer. Say it's a 4-to-1 mux. It has 4 inputs: I0, I1, I2, I3. You have 2 selector inputs, S0 and S1. So what you apply on S0 and S1 determines what is being routed to the output, right? If I apply a 0, 0 here, I got I0 being routed to the output. Very similar to your telephone exchange. You have 4 calls that are waiting. Depending on what the exchange, whatever you select by applying the right input at the selector inputs, you route that particular call, connect that call to the output. Okay. All right. Now the design approach was, so you have this, right? So these are the terminals. Again, these are this you can classify multiplexers as we have done in the last class into uh, medium scale integrated circuits, right? So I have these inputs. The only things that are available for me as a designer are these inputs. I can only access those inputs. I cannot access the logic gates that are present within the multiplexer. So whatever I have to do with those inputs and the outputs. Of course, my function should be the output here. So now what I will do is, again, going back to what design approach we have chosen last time, I would choose 2 of my inputs here from this to form my selector inputs. In last class, we have chosen A and B as the selector inputs. This class will choose C and D and see what happens. So those are fixed. So I've chosen them. Those are fixed. What that means is that C and D will not be appearing on these inputs anymore because those are fixed over there. So what appears here would be functions of A and B only. That's important to note. All right. Now with that, let's actually draw our K-map for this particular function. Again, the similar way that you know. And then we'll divide this K-map into sub-K-maps. Okay, so that's your A, B, C, D, 0, 0, 0, 1, 1, 1, 1, 0, 0, 0, 0, 1, 1, 1, 1, 0. And my function is 1, 4, 5, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So that's my function. Okay. All right. Now I need to divide this into sub K-maps. How should I divide this now? I'm using my CD as my selector inputs. My CD values are constant along these columns, right? Vertically, absolutely right. My CD values are constant along these columns, so I would divide my K-map into these individual columns. So each individual column would be my sub K-map in this case. I would use the exact same rules as K-map that we are accustomed to, but within my sub K-maps. Okay, and read out the product terms only in terms of A and B because C and D are fixed here. My product terms will now be only in terms of A and B. So let's do that. So in this case, that's a combination for this particular sub K-map. Again, this particular combination, whatever product term that you obtain here, where should that be applied to? CD 00, CD 00 would route I0 to the output, so whatever you get from here should be applied to I0. 01 would be routing I1 to the output, so that should be applied to I1. 11 would be routing I3 to the output, so that should be applied to I3. 10, which is 2, would be routing I2 to the output, that should be I2. Okay, and now here I have 4 adjacent cells, combine them into a single combination. Here I have 1 adjacent cell. Here I have no ones. What do I do? For 1, 0, this particular column, I don't have any ones. What would that product term correspond to then? A K-map with all zeros, right? Zeros, right? These are all zeros. I don't show them, but they are there. Ground, yes. These are all zeros. That means the product term I get here is equal to 0. That's all ones. That means the product term I get here equals 1. Here I have 2 ones. So I'll be looking at these. So what I'm going to get as a product term here is I keep the one that do not change, which is B. So that's B. Right? A changes, B comes out. And finally we have here, that corresponds to A prime B. Now I can write my function as I need to apply I0, I need to apply B on I0, so that when my CD is 0, 0, when my CD is fixed at 0, 0, my function is determined by what you apply on B. Okay. When I fix my CD at 0, 1, my function is determined by what you apply on I1, which is 1. In other words, 1. My ground, that's a 1. In other words, if I fix my CD to be 0, 1, then my function is basically 1. Right? If I fix my CD to be 1, 0, 1, 0, my function is basically 0 or ground. And finally, we have I3, which is this one. If I fix my function to be 1, 1, if I fix my S1 as 0 to be 1, my CD to be 1, 1, okay, then my function would be a function of a prime b. So what you apply on a and b, a function will be a function of a prime b. Then I fix my CD values to be 1, 1. And that's it. And if you compare this to the last class exercise, where we chosen A and B as the selector input, you will see that this particular implementation implements this function with fewer number of gates. So the choice of your selector inputs really matters, because that determines the complexity of your implementation. I hope that makes sense. Does that make sense? Any questions here? No questions? Okay. Now, before we move on to the next topic, now we're going to really switch gears. Okay. I would like to ask you if you want me to cover any concept for the exam that you want more clarification on. Oh, can we go over the difference between the flags? Okay, let me check. Can you be a little bit more explicit on exactly what difference? As in, okay, we have in the class we have covered 4 flags, right? In the class we have covered 4 flags. We have the Z flag, that's the 0 flag. My Z flag is true. The way we have configured the Z flag, my 0 flag is true if the sum bits of my adder are all zeros, right? So it indicates whenever I have, whether it's a subtraction result or an addition operation that results in a sum being all zeros, then my Z flag is set. It's like an indicator, right? It's a flag. You're flagging an operation. You're flagging an outcome, right? So that's how we define a Z flag. We also covered the C flag. The way we have defined it, we derived it through the cout, right, from the adder. The way we defined it is when we can think about the C flag as the overflow flag, right? If my C flag is set, implies that's an overflow operation. Overflow for what? For unsigned numbers only. So I'm working with unsigned numbers, whether it's subtraction or addition. If my C flag is set, that indicates that that's an overflow. Okay. I can also use it as a borrow flag. Borrow flag. This is useful when I'm trying to do comparison between, again, unsigned numbers, confined to unsigned numbers. When I'm doing A minus B operation, A and B are 2 unsigned numbers. I'm looking at them as unsigned numbers. And then if A is less than B, that means if I want to perform this operation, then B has to borrow from an imaginary borrow, right? Otherwise, I'll not be able to do the subtraction. And that indicates that operation is indicated by the C flag. The C flag is set every time I have to borrow from an imaginary borrow. So every time my C flag is set, when I'm working with unsigned operations or unsigned numbers, a subtraction operation, that indicates that my A is less than B because I have to borrow from an imaginary borrow. Okay. Yes, absolutely right. So C flag and the V flag, so working with C flag, that indicates an overflow only for the unsigned numbers. I can use C flag to indicate an overflow operation for unsigned numbers. That's absolutely right. So we had the N flag, that's the sign flag. So these are the set of flags we use for signed number operations, signed numbers, and then we got the V flag. So these 2 flags, along with the Z flag, we'll use them for signed operations. When I'm trying to perform this comparison between signed numbers, okay, or various other signed operations, additions and subtractions. I'll use the Z flag, N flag, and V flag to make those decisions. Whereas for unsigned numbers, I'll be using the the V flag and the C flag. Okay, does that make sense, Garrett? Are there any other questions you have or any other clarifications? Okay, good. All right. When we did the BCD adder, okay, that's good that you asked a question. V and N flag. Okay, so before we move on to the next, so N flag is the sign flag, right? That's the most significant bit. That basically we use the most significant bit of the sum of the from the adder as our sign flag, right? So that's the sign flag. The V flag indicates the overflow operation. Overflow. Remember how we did this in the last class? We did this as C out, exclusive OR with C out minus one, or so that's the C out from the most significant bit. You can consider this as a C in to the most significant bit. Every time that's equal to 1, or in other words, if my C out and the C, otherwise the carry out of the most significant bit and carry in to the most significant bit are not equal, then we have the overflow condition. We have derived it in the class. Right? So the N flag is the sign flag, V flag represents the overflow flag. And a combination of N flag and V flag would allow us to determine the relative magnitude between A and B, where my A and B are sign numbers. All right.
And C out minus one, is it minus one in the subscript?
Yes, in subscript.
Okay.
Not, yeah, C out minus one in the subscript. That's absolutely right. So that's the carry into the most significant bit. That's the carry out of the most significant bit. I don't know what would be a better way of representing that.
Thank you for the clarification.
Okay, yeah, absolutely. Okay, so now let's go to Yusuf's question. So you have, okay, so the question, you can already see that, right? So for BCD, when we derive the BCD adder, we examine the way it works. If I want to derive the BCD adder using just the binary adders, I quickly realize that I should be using a 4-bit binary adder, right? Because each decimal digit is represented as a 4-bit BCD, right? Or a 4-bit binary code, which is the BCD, binary coded decimal. Okay. So when I'm adding two digits together, that means in other words, I'm adding 4 bits together. Each digit being added corresponds to 4 bits being added, 4 binary bits being added, right? So why can't we just choose, instead of trying to design everything at the gate level from the scratch, can I use existing 4-bit adders to do that? And that's exactly the approach that we have taken. And we realized that when I do this, I get the right BCD sum. I get the right sum in the right BCD format every time my sum does not exceed 9. However, when my sum exceeds 9, I get the wrong representation. The sum itself is right. It's because it's the binary sum itself is right, but the representation is not corresponding to the right BCD representation. So I have to do some adjustments. And the way we have looked into that, right? When I'm adding two 4-bit binary numbers, okay, let's say A3, A2, A1, A0, B3, B2, B1, B0. Okay. When I'm adding two 4-bit binary numbers, I get a carry out only when my sum exceeds 15, right? I get a carry out of 1, let's say carry out, and sum C3, C2, C1, C0. When sum exceeds 15. Now, if my A3, A2, A1, A0 are are supposed to be my BCD digits. Again, I'm trying to apply them to a binary adder. The binary adder doesn't know that what I'm applying are BCD, right? So it basically assumes that it's just binary and then gives out the sum, a binary sum, right? Now, when I'm trying to add these binary two, in this case, BCD digits, binary coded decimal digits, I should be getting a carry out when my sum exceeds 9, right? That's how decimal addition works. In decimal, when you're doing decimal addition, I get a carry out every time my sum exceeds 9. So there's a discrepancy here. So sum exceeds 9, I should get a carry out. But here, I get a carry out only when the sum exceeds 15. That means I need to provide that excess. So every time my sum exceeds 9, I need to displace it by 6 so that I get a carry out. I can generate a carry out and get the right format for the BCD. So what is the difference between 9 and 15 or 15 and 9, which is 6, right? So I need to basically translate the binary sum by 6 to get the right BCD format. Does that make sense? Okay. Now in the exam we had a base 7. Oops. Base 7 adder. Okay. Now for base 7 I need at least 3 digits, right? 3 bits to be representing a base 7 digit. Does that make sense? I need at least 3 digits or 3 bits, binary bits to represent or to encode a base 7 digit. Why? Because if I'm working with base 7, my digits goes from 0 to 6, right? 6 is my largest digit, and to represent 6, I need at least 3 bits. I cannot go below 3. I have to have at least 3 bits, right, to represent 6. All right. Now, if I want to design a full adder that can work with base 7 full adder, for example, okay, so I can basically work with existing binary adders. So what size binary adder should I be using here for base 7? A 3-bit binary adder. That's absolutely right, because I have 3 bits. So I need to use a 3-bit binary adder. So when I'm working with 3 bits, 3 binary, so when I'm adding 3 binary bits, A3 or A2, A1, A0, B2, B1, B0, after what sum will I be generating a carryout? After 6? No, for a binary adder, basically I'll be generating a carry out after 7, right? I get this, and then this is again, remember, that's the binary sum. That's 7. I'll be generating a carry out after 7. When I'm adding 2 3-bit binary numbers, I'll be generating a carry out after 7. Okay? With me until this point? Does it make sense? I'm not talking about base 7 at this time. I'm just looking at 3-bit numbers, 3-bit binary numbers, adding them together. I'll generate a carry out only when my sum exceeds 7. Right? However, if I want to get the right binary coded base 7 sum and apply, and I'm trying to get the 3-bit, I'm trying to get it using existing 3-bit adders. Okay, so I'm adding, in this case now, B2, B1, B0. In this case, now I'm considering these as my 7, or base 7, digit, okay, that is encoded as a 3-bit binary number. Okay. Now when I'm adding these two together, two base 7 binary encoded base 7 digits, I should be getting a carry out when my sum exceeds what? See out when my sum exceeds what number? After, is it after 7 or after 6? After 6, right? Because for base 7, my digits goes at 0 to 6. The next, after that, the next sum will be 1, 0 for base 7, right? Okay, does that make sense? When I'm working with base 7, because my digits go from 0 to 6, the next number in base 7 will be 1, 0, which corresponds to 7. This value is 7, 1, 1, and so on. So, in other words, when my sum exceeds 6, I should be generating a carry out. When I'm adding these two bits, or these two base 7 numbers, I should be getting a carry out every time my sum exceeds 6. Otherwise, sum is less than 6, less than or equal to 6, I don't have to do anything. My binary sum and the base 7 sum are equal. However, the discrepancy comes when my sum exceeds 6, when I'm working with base 7 numbers. So, how much should I be adding to this sum, to this binary sum, to make it equal to the base 7 sum? Again, here I get a carry out after 7. Here I get a carry out after 6. The difference is 1. To make up for that difference, I should be adding 1 to the base 7 sum, to the binary sum, where I'm applying my base 7 digits to the binary adder. Every time my sum exceeds 6, I need to add 1 to my binary sum to get the right base 7 format or formatted sum. Does that make sense? And now your design basically collapses into designing this control logic that sees, okay, I'm getting this sum, is the sum larger than 6? The sum is larger than 6, you output a 1, and then you design your 3-bit, your 7, the 7 or base 7 adder. Yusuf, does that help? Would you be able to do that from now? I mean, from this point on, you should be able to design it, right? Any further questions on that? So that's good. So you're able to understand what should be added and so on. So what I'm going to design then, you're basically going to design this control circuit that takes in the C out of the binary adder along with the sum S3 star, S2 star, S1 star, S0 star, and compute what is called the K out, let's say. That's the control logic. All it's doing really is looking at these values and determining when my sum is exceeding 6, and outputs a value of 1 every time my sum exceeds 6, and you need to design that logic with these inputs applied. Okay. How many of you got the ternary adder circuit using the modular approach? Just raise your hand. Okay. 24. Okay. So what I'm going to do is I'm going to post a video solution of that problem. So hopefully by looking at that, you'll have better idea working through this. Okay. that still counts. I mean, as long as you got it, you got it. So that means you're one step well prepared for the exam. Yeah, Jacob, you have a question? Okay, that's fine. So does that make sense for the design of the 7-bit adder, or the base 7 adder? Yes, I'm going to post the video solution for that. So you should have that will help you. Okay, any other clarification? Yeah, very good. Any other concept to be cleared? So my suggestion is, now you have base 7, base 10, base 10, and base 3. You have 3 adders as examples now, right? And I would really like you to practice it more and more times, so that if you find similar problem on the exam, most likely you will, you don't have to think too much. You can just do it within 10 minutes. Okay, so you practice it multiple times until you're sure that you've got the sufficient expertise. That means you have a good conceptual understanding of the problem and the solution. Now you will be able to apply it to any other problem. Okay, on Thursday, this Thursday. Yes, that's absolutely right. During class time. All right. Any other questions, concerns so far? Okay, if not, let's should we move on then? The next topic. All right. So since I'm not hearing anything otherwise from you guys, so let's move on then. So now we're going to really shift some gears. So far we have been doing this, right? We're looking at the combinational logic. And what does that mean, really? So far we have focused on designing systems, these blocks, okay? When we know what the input and output relation should be, you're basically designing these systems where my functions are outputs, my outputs for this system are functions of some combinations of some logical combinations of my inputs A, B, and C, D, and I derive my function. I get the functionality, and all the circuits that we have discussed so far in the class, these are all essentially combinational circuits. Okay. Now, if you notice, for all these circuits, my output only depends on what has been applied at that present instance to the system, right? It does not depend on any other factors. It just depends on, similar to a switch, light switch that we have taken before, the example of a light switch. The state of the light switch, whether it's on or off, depends on what is the state of the switch. Whether if you turn it on, the light turns on. If you turn it off, the light turns off, right? It does not depend on any other attributes, as in this particular situation, it does not depend on the history of the location of or the position of the switch. And it only depends on the current position of the switch. So all of the circuits are similar to that, where my output only depends on the present input. Okay. Now the question is, can I be able to design anything and everything with the knowledge that we have so far? Right? Now, again, ultimately what we want to do from this class is to see how we can actually design systems or hardware that can be programmable. Of course, in the last class, we went one step ahead in our goal by describing how to take decisions, how to make the hardware or how to enable the hardware to take some decisions during a program. When I say program, of course, we did not really go into specifics there, right? When you write a program, and you must have written some kind of a program before, you write a program and then you basically compile it and then let the computer run it. So the way that works is, you have a sequence of operations or sequence of instructions, and you want the computer to basically run through the sequence of instructions and execute the code, right? You've written a code, and you want or you expect the code to be executed by the computer or whatever computing device you're trying to program, right? That means it has to run autonomously. That means once you've written the code and then you run it, you don't have to basically come back again and try to insert yourself into the execution routine. So everything else is once the computer code is written and executed, you're no longer needed in the picture. The computer basically runs it all by itself, going through that sequence of instructions one at a time. Okay? And in the meantime, and as it runs through the code, it also takes the decisions, and it's basically all autonomous. So how does it work, right? Now, with the knowledge that we have in the design of combination circuits, would we be able to design something that can actually be made to run sequentially, step by step? Okay? And the answer is no, right? We don't have any means of ensuring that my device, whatever hardware I design, can be made to run or made to execute instructions in a sequential manner. Like at this particular instant of time, okay, I'm going to execute this instruction, and the next sequence or in the next time period, I will be executing the next instruction, and so on and so forth. Just take an example of a simple programmed device that you use all the time. A simple example would be your washing machine, right? Obviously, that is programmed, must be having some microcontroller there, which programmed it. So yeah, it came with the programmed code. Now, as a user, all you have to do is you load your clothes in that machine, you apply your detergent, and you hit the start button, and then you expect that to run through a sequence of, I would say, uh, states, right? So initially, you have the fill state where that particular machine is filling it with water. So you have a program that is written to open the valves for the pipe, and then the water comes in, and it fills it for a certain amount of time, right? Shuts off, then it runs into a different state, the wash cycle or rotate cycle, and so on and so forth. So it's basically autonomously programmed. So basically, you don't have to come back as a user, insert yourself, and keep pressing buttons all the time, right? If it was designed simply using combinational logic, it could be done. In that case, your intervention would have been necessary. Basically, you would come there, you would design a particular control module that takes in some inputs, and this output can control the valve. You press a button, and then those inputs are applied, and it turns on the valve, turns off the valve. So every time you have to be there pressing the buttons. Right? Now, if you were to design the washing machine just by using combinational logic, the things that you have learned so far in the class, obviously we don't want to do that. We want to be building programmable systems that can operate autonomously. A simple example is the washing machine. So, what are the key things or key Lego blocks, if you will? We call that the Lego block because we have been using this example. What are the key Lego blocks that is missing in our discussion so far? The knowledge of which would enable us to design these programmed devices. Memory, very good. One aspect is memory. Of course, we need this memory so that we can, first of all, we can put the code in memory so that this washing machine has a sense of where it stands in its cycle, right? And once I know where I'm standing, where I'm at in a particular cycle, now I know what my next cycle should be, right? All right, what else? I need some form of timing information as well. Because as you can see here, this washing machine, in the same example, it's advancing in time, right? It's performing a particular operation at a given time. It performs it for a certain amount of time, and then it goes to the next operation after certain time. So you need to somehow incorporate the sense of time into these devices as well. So timing is also, with the current knowledge that we have, these are the two missing blocks uh, that are missing still. The knowledge of which, once we know how to incorporate those, we'll be able to actually design these machines that can be programmed, that can be, you know, um, more autonomous. All right. So let's start with one thing at a time. Let's start with memory. How to design memory. Now, before we actually do that, let's think about memory and see what it actually means. Because once you know what we need to design, then we can think about actually designing something, right? So, what is memory then? Let's not get very technical at this time. So, how would you define memory? What is that? What does that mean? What do you mean by memory? Maybe, I mean, it's not a word that you're looking at, you're seeing it at this very first time. You use it all the time. You know what memory is. So, if I want to ask you to define it in your own words, it doesn't have to be very technical. How would you define it?
Retained information.
Recalling information. Okay, that's one of the answers. Okay, retained information. That's also a valid answer. That means if I want to expand it, if I want to, go deeper into that, what that means is, again, the same thing here. If I want to recall or retain some information, what that really means is, if you can imagine, if I'm talking about, yeah, let's actually talk about memory in this way. Obviously, you have some memory, right? Your brain, you can store information, you can recall information, right? Now, for example, we are having this class, okay, or we have had many classes, and so in this case, I am the source of information, and you are the recipients. You're looking at my class, and I'm speaking. I'm trying to put some knowledge in your memory, right? And once this class ends, what's happening? Your source of information is getting lost, right? Once the class ends, I'm no longer there. However, what information I wanted to put in your brain, hopefully I put some information in your brain, that information would at least be available for a certain amount of time. That information is retained for some amount of time, right? Even in the absence of the information source. So that's the difference between combinational memory, where the source has to be always present, versus the memory unit, where, even after I take out the source from that memory unit, that information that was placed in that in that unit is still retained, right? I hope that makes sense. So source, as in, I'm the source here. So in other words, let's now talk about memory at the very fundamental level. If I'm, again, the beauty about digital systems that works on binary is that if I can implement, if I can construct uh, a unit that can store a single bit of information, right? Because my information, when I'm talking about this class, it's all zeros and ones. Zero is as good as one, right? It's not like zero has a less priority than one. Zero and one have equal priority. Basically, that's information. And if I'm able to store a single bit information in my unit, then through modular approach, if I want to make it into an n-bit memory storage, all I have to do is, just copy and paste that particular module that can store one bit in n times. And now I have basically an n-bit storage element, right? So very modular approach. Okay, so now let's say that's the information source. That means that's the input by which I can actually access this. Let's say this is a node. Again, we talk about nodes, right? Nodes can hold potentials, voltages, and those voltage value on the nodes could be 0 or 1. Okay, so let's say I'm designing something, let's say having a single input like this, and that's the node. Let's say I place a 1, let's say that's my information source. Okay, at a given instant of time, I place a 1 here, which would basically change the value of this node potential voltage to be a 1. Okay, and the idea here is when I take out the information source, I'm not applying anything now. That value of 1, the node voltage still retains. And then we call that, yes, this particular thing acts like memory because in the absence of the information source, whatever I put there still remains. Okay, does that make sense? At least the basic definition of, or at least the fundamental way of looking at this. Okay. Now there's an issue with this though. The issue is if I want to store a 0 with a single input, right? When I say taking out the information source, that means I had a 1 applied. If I take it out, which basically corresponds to applying 5 volts there, right? 1 corresponds to high level, 5 volts in our, and that stores a 1 on my node. Now what does taking out the information source mean? That means I'm applying a 0, right? Taking out the information source means I cannot just let it float. I either have to apply a 1 or a 0, but again 0 is also a data. So how can I distinguish between taking out the information source and applying a 0? So there's a problem here. Do you see the problem with a single input like this? I have a problem here. If I want to store a 1, which is fine, I'll just apply 5 volts on my information source, then that stores a 1. And then I want to take out the information source. I took out the information source, but then that corresponds to 0. That's grounded. So how can I distinguish between what I want to store here? Or in other words, how can I distinguish between taking out the information source and applying a 0 to be stored? So we have a small issue here, small problem here that we need to resolve. But before I move on with how do we resolve this, do you see what the problem is with this approach? Any questions on that? Because I need to make sure that you get it this first before we can actually start resolving it. Vikas, what do you think? Okay. All right. This could be a potential solution. So instead of having a single input as a source of my memory, what about having 2? Let me call it S and R for now. S corresponding to a set input, R corresponding to a reset input. Okay. Now, if I want to store, let's say, a 1 in my location, in my node, here, call that the memory node. If I want to store a 1 there, what I will do is I'll place S equal to 1, R equal to 0. S equals to 1, R equal to 0, stores a 1 on my node. And now I want to take out the information source, right? Now what is that? Now with 2 inputs I can do that. If I want to take out the information source, I'll come back. put both of them zeros. And if I want, and then that would correspond to taking out the information source. And I want this unit to recognize that configuration and still retain that one that was stored before. Okay. Now, if I want to store a zero at a different time, I'll come back to my memory unit and I will place s equals 0, r equals 1, store 1. Let me just explicitly write this. Store 0. S equals 0, r equals 1 at a different time. Then that will basically store a 0 on this node. Again, taking out the information source corresponds to, placing s equal to 0, r equal to 0, grounding both of those pins. And I want my device to recognize this as the memory state. So whatever was stored before, which was 0, would still retain as 0. So with two inputs, I may be able to do that. With one input, we had this issue of, distinguishing between taking out the information source and storing a 0 in my memory location. With two inputs, now I have more control on those. Now I can define how to store 0, distinguish that from defining how to distinguish that from defining what it means to take out the information source. Okay. All right, now let's see if we can design a circuit that would kind of work like that. So it's a very primitive memory cell, if you will, that can store a single bit of information. And as I mentioned before, if I can do that for 1 bit, I can do it for any number of bits. Just a matter of copy and pasting those units multiple times. Okay. All right, so let's start to actually look at the design of the single bit memory unit. Okay. So let's examine this circuit. I have two NOR gates. So far, we never saw any circuit that consisted of a feedback, but now we will start looking at circuit that can have some feedback. Here I have the output of one of the NOR gate going as input of the second NOR gate. So we call that 1 and 2 NOR gates. And the output of the second NOR gate going as the input of the first NOR gate. So we have not analyzed any circuits like this before. Before, we never had a feedback from the output to the input. So the analysis was very simple. All I had to do was just draw the truth table, and then we could get the analysis done. The analysis here is a little bit more involved. So let me call that R. Let me call it S input. Let me call this Q prime for now. Okay. And you'll see exactly why we do that. So how do we analyze this circuit? Can I do a truth table? If I look at this outputs and inputs, I have two outputs, two inputs. Can I do the truth table between S and R to get to define my Q and Q prime? It's not as simple, right? Because now my other input to this gate is an output. Now I don't know what output is. So how do we analyze this? Right? You see the problem? Okay. So let's do this then. To be able to analyze this, we have to have some value here. These two input terminals. So that means I need to assume something and see that for different assumptions, how does that output change for different values of the applied input? If I assume some values on Q and Q prime, okay, how does those outputs change for different values of the inputs? So that's the approach we're going to take now. Okay. All right. So let's assume that. let's assume that Q was 0 to start with. So when you just came to your lab, you have this circuit configured, okay, and you don't know who was there before you who did the lab. So you come to the lab and then you measure this, and you measure them to be 0 on the Q, 1 on the Q prime. Okay, so that's what you measure. And now you come and apply some values here on S and R. Okay, let's put some values. Let's say S equals 1, R equals 0. So I'm putting S equals 1, R equal to 0 on these terminals. And for this, if we want to analyze this, we need to, of course, know the truth table for an OR gate. So let me put it for your convenience here. If I have two input NOR gate, where my inputs, again, so these are all possible combinations. And my function is true only when A and B are both zeros, right? That's the truth table for an OR gate. All right. So now I'm applying a 0 here, 1 here. When I just came to the lab, I measured these outputs. I measured them to be 0 and 1. In this case, that will be a 0. That will be a 1 because that's the feedback, right? So that 0 is being fed back as an input to this gate. This 1 from Q prime is being fed back as an input to the next gate. All right. And now I can analyze this. So now I have 0 and 1 as the inputs to the gate 1, NOR gate 1. 0, 1 should make this 0. That's still 0. Okay, so that's good. That doesn't change. But here I have 0 and 1 applied to this NOR gate, right? And that would change the output now to a value of 0 again, right? Because 0, 1 should change that to 0. So now the value is updated to 0. And immediately this particular value is being applied here. The value of 0 is being applied here. Now 0 and 0 on my NOR gate makes the output to be a 1. So that value is now updated to 1. Right? And now this one is being applied here. That's 1 is being applied to this gate. And now I have 1, 1 being applied on this gate. 1, 1 is still 0. So that 0 is not changed. 0 is applied here. 0, 0 makes it 1. 1, 1 makes it 0. So now that system has reached a steady state. So no, the values are no longer changed. So these values are my new outputs when I apply S equals 1 and R equal to 0 input. Okay. Now what I will do is, okay, I've done that. Now I come back to this circuit. I know exactly what these values are. Q equals 1. I measured it now. Now I go back to this circuit and change my S to be a 0 and R to be a 0 as well. So I go back to the circuit, change those values, and see what happens. So now I'm changing S equal to, instead of 1, I change that to 0. What's going to happen now? Again, 0, 1. 0, 1 makes it 0. That's not changed. And then 0, 0 makes it 1. So that's not changed either. So those values that were there, that we obtained, the new values that we obtained by putting S equals 1 and R equal to 0 before, and then when I take out these values, when I put S equals 0 and R equal to 0 on these input terminals, these values are no longer changed. These values remain as 1 and 0. So it's already, you can see the performance of this particular simple circuit resembling what we wanted to achieve, right? When I put S equals 1 and R equal to 0 on the block, I wanted to store a 1. And when I take out the information source by placing S equal to 0 and R equal to 0, I wanted to put that 1 retained in that node. So if I consider this as my memory node, right? That value is retained even after I'm taking out the information source. Do you see that? Now we can try for s equals, let's say I come back. If I want to store a 0 on my memory node, what I will do, I will come back at a different time. Okay, let's say these values are not changed. That means I come back next day. So these values are not changed. I come back next day and then apply r equals 1 here, s equal to 0 here, and see what happens. When I do that, I have q equals 1 being applied here. So 1 and 0 makes it 0. So that's still 0. Nothing changed there. But here I have 0 being applied and 1. 0 and 1 makes this 0. Right? According to my truth table, 0 and 1 makes that 0. So that value is updated now. So that changes to 0. Right? So now 0 is being applied on my second gate. So now I have 0 and 0. 0 and 0 makes that 1. So that value gets updated to be a 1. And this 1 is being applied here. Now 1 and 1, 1 and 1 makes this 0. So that 0 remains. And then 0 and 0 makes that 1. So that 1 remains. And now I've reached the steady state, a new steady state, where my values are updated. My q is now 0, q prime is 1. When I did the change at the inputs, right, r equals 1 and s equal to 0, my output values are changed. Again, going back to the similarity between what we wanted to achieve and what this particular circuit is doing, right? Remember, when I did r equals 1 and s equal to 0 on the block that we wanted to implement, we wanted to reset the memory location. So this node is now reset. The node value now reads 0. And now if I take out the information source, how do I do that? I go back and place r equal to 0 here. S is already equal to 0. Let me see if those values are retained. So now again, 0, 1. 0, 1 makes it 0. So that's 0. Nothing is changed there. 0, 0. That's 1. No change. So now those values are retained. Right? So now I'm able to store a 1 on this node by placing s equals 1 and r equal to 0. I'm able to retain that value even after I take out the information source, right? By placing s equal to 0 and r equal to 0. I can rewrite a different value like a 0 by placing r equal to 1, s equal to 0. I change the value to 0. I can keep that value by taking out the information source, s equal to 0, r equal to 0. So now it already performs as a simple primitive memory cell. Okay. Now, of course, we cannot analyze this using truth table anymore because now I have an output dependency, right? I have my output, my values. If I want to analyze this, it depends on the previous value in the history of the values. It depends on my q and q prime being applied to these inputs. So I have to have prior knowledge about what these values were to be able to analyze this circuit. Does that make sense? Of course, these values depend on the prior inputs. So in this case, my circuit depends not only on the present inputs, but it also depends on the history of the inputs, just as you have seen here. And that leads us to the next topic of the design of sequential circuits. Sequential, because these are circuits can perform a sequence of operations, a programmed sequence of operations. These can be run through a set of sequence of operations. And for these to work, these circuits, the output depends not only on the present inputs, but also on the history of the inputs. Okay. Okay, let me take a pause and let me see if you have any questions. Does that make any logical sense? Are you with me until this point? Okay. All right, very good. All right, to summarize, this is what we have done so far. Okay, let me just put everything into as a summary. I should not have taken that out. S equals 0, S equals 1, R equals 0, places Q to be a 1, right? That's the set state. S equals 0, R equals, that was followed by R equals 0, maintains Q to be a 1. So that's the memory state. Again, remember that I'm following this sequence here. That was the first input, that was second input combination. S equals 0, R equals 1, change my Q to be a 0. Again, S equal to 0, R equal to 0, maintained my Q to be a 0. Again, that's my memory state. So as you can see here, before if you recall, for the combinational circuits, for a particular set of inputs, the output is unique. I can only define a single output. But here, for the same set of inputs, I have two instances where I have the same set of inputs, I have different outputs, because that depends on the history now. Okay, so that's a characteristic of a sequential building block. Okay, that depends on the history of the inputs. All right. And if I want to describe the system, then I do that using what is called the characteristic tables, not truth tables anymore, because we have that dependence on the history. These are called characteristic tables. Characteristic tables. Okay. Now, what about, we have not, again, we have the freedom to do whatever we want to S and R, right? We can apply whatever we want. We want to apply S and R. We haven't, until this time, we haven't seen the S equals 1 and R equals 1 condition. Because again, that's something that we are free to do. So the inputs are available to us. We can apply S equals 1 and R equals 1. Right? And what happens when I apply S equals 1 and R equals 1 for this particular circuit? So now I'm coming back to the circuit. I'm applying S equals 1, S equals 1, and R equals 1. Okay. That's my history. Applying S equals 1 and R equals 1. What will happen to my Q? For a NOR gate, if I have one input to be a 1, then the output goes to 0. So that remains as 0, still remains as 0. Here is the 1, I have 0 and 1. One of the input to the NOR gate is a 1. That means the output should go to 0. So obviously my designation, I have a problem with the designation here. Until now, my Q and Q prime behaved very well as Q and Q prime, right? If Q was 1, my Q prime was 0, Q was 0, Q prime was 1, so they were complementary. But in this case, of course, my Q and Q prime remain, naming convention fails in this particular instance. Now I come back and say, I apply S equal to 0, R equal to 0. Supposed to be my memory state, and let's see what happens now. So I come back to this circuit, apply 0 here, apply 0 here. Now, how do we analyze this circuit now? Okay. But before we analyze this, here's the critical thing that you need to understand. Even though you fabricate these, when you're trying to fabricate them, right, on a chip, like an integrated circuit, even though you try to make them as identical to each other as possible, there will always be certain small differences between the gates. When I say the differences in terms of the switching speeds, how fast it switches from 0 to 1, 1 to 0, right? We talk about the switching speeds. Now, one gate between those two gates, you'll always have one gate that is slightly faster than the other gate. Okay. And for this particular instance, that individual speed of the gate really comes into picture. Since we are almost toward the end, what I will do is I would like you to analyze this last part, this condition where you put s equals 1, r equals 1, and followed by that, if you do s equals 0, r equal to 0 on the inputs, what happens to the outputs? I would like you to analyze this and report this in the next class. That means that's going to be next Tuesday. Okay, and then we'll pick it up from there in the next class. All right. So with that, let's stop the discussion here. Good luck with your test. Do you have any other questions, concerns? If not, I'll see you guys on Thursday for the test.